Have you ever wondered what space sounds like? I know, sound can't travel through a vacuum, but that doesn't mean the universe is silent. Quite the opposite, filled with different vibrations just waiting to be decoded. Through a process known as data sonification, scientists can turn data on plasma, X-ray, and even gravitational waves into something we can actually hear. In past videos, we explored the haunting sounds of Saturn, Earth's magnetosphere, and the Sun's solar flares. But today, we're heading headfirst into the most terrifying sounds space has to offer, from the ghostly wail of a passing comet to a growling supermassive black hole, to the echoes of a black hole collision from 5 billion years ago. So, what do these phenomena sound like? And what do their sounds teach us about the cosmos? We're about to find out. I'm Alex McColgan and you're watching Astrum. Join me today as we tune into 4 of the scariest sounds in space. We'll explore how scientists have captured these bizarre sounds and why they matter. As the saying goes, in space, no one can hear you scream. That's because sound waves require a medium to propagate, and vacuums are, well, mediumless. But other kinds of waves, such as radio, plasma, X-ray, or gravitational waves, can be converted into audio through data sonification. But the results are more than just cool sounds. Each audio clip carries distinct and important information about celestial objects and phenomena such as solar winds, pulsars, and black hole collisions. Just as data visualization lets scientists spot patterns more easily, sonification allows researchers to detect patterns, trends, or anomalies within complex datasets. You might have seen one of my videos about sounds in space before. They mainly focused on planets and the sun. But today I'll be sharing newer findings from more obscure places, like the first successful probe landing on a comet and a supermassive black hole in the Perseus cluster. Before we get there, our first stop on this audio tour is a little closer to home. If you've been watching this channel for a while, you might remember my video on the sounds of Saturn. Here I want to focus on its spectacular rings, one of the landmarks of our solar system. Saturn's rings are made up of countless particles of rock and ice. Most of these particles are electrically charged, mainly due to the ionizing effect of solar radiation. Saturn's magnetosphere is also filled with charged particles, which are free to move, interact, and form other complex phenomena. They aren't fixed in one place. In a nutshell, when charged particles in Saturn's rings interact with the plasma in its magnetosphere, they experience what's known as the Lorentz force. This force makes particles spiral around the magnetic field lines and create oscillations in the plasma, also known as plasma waves. In 1997, NASA launched the Cassini probe to study Saturn up close. One key part of the mission was to explore Saturn's ring-plasma interactions more deeply. As the spacecraft passed through Saturn's ring system, its radio and plasma wave science instrument recorded the waves produced by the charged particles in the rings. This instrument is incredibly sensitive, so sensitive it detected lightning in Saturn's atmosphere from thousands of kilometers away. Saturn's thinnest rings contain dust particles just 200 nanometers large, the size of a virus. When these dust particles collide with the instrument's detector, their impact creates tiny puffs of plasma. The plasma impacts are then converted into sound, allowing scientists to hear the electromagnetic interactions taking place. And the results are totally eerie. It feels like the kind of thing we as humans aren't even supposed to hear. Here, have a listen. But there's more. In 2017, Cassini's grand finale orbits captured one particularly haunting recording of plasma waves moving from Saturn to its moon Enceladus. What makes this clip more haunting is that it was one of the last clips ever sent back by Cassini. 2 weeks later, the probe was deliberately plunged into Saturn's atmosphere after 20 years of loyal service to humanity. Imagine this being the last thing you'll ever hear. Cassini wasn't the only probe to send us back data on vibrations near a celestial body. In 2014, ESA's Rosetta probe sent back some trippy data on a passing comet you won't want to miss. Our second stop is Comet 67P, the object of ESA's Rosetta mission. It is the first and only comet to be successfully landed on by a man-made lander. Comet 67P orbits the Sun in the outer solar system roughly every 6.5 years, and it is thought to house several primitive materials from the formation of the solar system over 4 billion years ago. On top of studying these materials, Rosetta's mission was to understand how solar winds affect the comet's coma and tail. To do this, they armed the spacecraft with a suite of plasma detection tools, including the Langmuir probe, to measure the electron density and plasma oscillations in the comet's environment, and a magnetometer to detect magnetic field fluctuations caused by these plasma waves. Together, the data provided a comprehensive view of the plasma dynamics around the comet. But this in itself wasn't a breakthrough. Magnetic field sound waves had already been detected from other comets, including the famous Halley's Comet. What was special about Comet 67P is the actual sound it made. Comet 67P's song was very different to the sounds measured from other comets before it, suggesting it had very different physical properties. I'll play it for you now. What's interesting is that this audio can be broken down into distinct components. The rhythmic clicking sound represents the periodic fluctuations in the plasma's density and the way the comet's magnetic field is distributed by solar wind. The humming parts of the sound reveal the continuous oscillations within the plasma environment. Here, I'll play it for you one more time. Honestly, to me it sounds like a Demogorgon from Stranger Things. Speaking of Stranger Things, our third stop on this tour is the closest thing we have to an upside down in this reality. Ever wonder what sound a black hole makes? Buckle up, we're about to find out. Travel some 240 million light years from Comet 67P and you'll end up in the Perseus galaxy. At its center lies one of the largest known black holes in the universe, estimated at a whopping 17 billion solar masses. Supermassive black holes like this one tend to emit intense X-ray and ultraviolet radiation due to the searing hot gas in their accretion disk. We're talking millions of degrees Kelvin. NASA's Chandra X-ray Observatory is a space telescope in high Earth orbit, tasked with looking out for X-ray data that might give us insights into the nature of black holes. It carries a highly sensitive electronic detector that captures incoming X-ray photons and converts them into digital signals, which lets scientists map the hot gas distribution of black holes, supernova remnants, and galaxy clusters. In 2003, it captured some tantalizing data. Chandra's high-resolution imaging and spectroscopic capabilities allowed scientists to study the X-ray emissions from the black hole and surrounding hot gas in the Perseus cluster. In 2022, scientists revisited this X-ray data and translated the frequencies into sound. By complete accident, they stumbled upon the lowest frequency sound ever found in the universe, a droning B-flat note 57 octaves below middle C. At such a low frequency, the period of the sound wave coming from the black hole is 10 million years long. Humans can't hear anything with a period longer than 50 milliseconds. Through data sonification, NASA scientists transposed this black hole song by a factor of quadrillions into the audible range for humans. The results? A tormented, guttural sound that'll make the hairs on the back of your neck stand up. Here, see for yourself. Creepy, right? But what does it actually teach us about the science of black holes? Many things, but perhaps most interesting is its implication on galaxy cluster evolution. In a galaxy cluster, which can contain anywhere between a few hundred to several thousand galaxies, the spaces in between are filled with thin gases and plasma, also known as the intra-cluster medium. It's much hotter and about 6 times denser than the gas found outside galaxy clusters. One theory is that the sound waves emitted by the black hole are actually partially responsible for the temperatures in the intracluster medium, since they carry energy. And since we know star formation is partially regulated by temperatures, it's therefore possible these waves play some kind of role in the evolution of galaxy clusters over time. Our fourth and final stop is something of a triumph. Even Einstein doubted humanity would ever be able to detect what I'm about to show you. If he were around to watch this video, I think he'd absolutely freak out. Back in 1916, Albert Einstein predicted that black holes emanate gravitational waves. Imagine throwing a rock into a pond. The water ripples. You can think of gravitational waves like those ripples, except instead of acting on water, they act on the fabric of space-time, ever so slightly stretching and contracting it as it passes. These disturbances were predicted to be so small that even Einstein himself didn't think humans would ever be able to detect them. Fast forward to today. In just over a century, we've managed to build a global network of observatories that have picked up on gravitational waves from about 100 cosmic events. For example, there's the Laser Interferometer Gravitational Wave Observatory, or LIGO in the US, the Virgo in Europe, and the Kagra in Japan, which all work together to corroborate data and pinpoint the wave's direction and source location. If you aren't familiar with their setup, the way these instruments work will surprise you because they are nothing like traditional telescopes. They don't use lenses, instead they rely on something much more fun: lasers. Scientists send lasers down 2 perpendicular tunnels several kilometers long. When gravitational waves from space arrive at Earth, they cause tiny disturbances in the fabric of space-time, which is picked up by these lasers. And I mean tiny. Something like 10 to the power minus 18 meters, or 1/10,000th of a proton. As the laser's paths are stretched or contracted by the gravitational waves, they emit different frequencies, kind of like the strings of a guitar. A higher frequency is a higher pitch. Converting this data into sound is how we get the signature chirp of a black hole collision. Each collision has its distinct personality. Long, low buildups, like this one, indicates a slower collision between pretty lightweight black holes. Faster, heavier black holes sound more like this. You just heard the sound of two black holes combining to form an even bigger black hole 5 billion years ago. It's the most massive and distant gravitational wave source ever observed, emitting about the energy equivalent of 5 solar masses in gravitational radiation. Pretty epic if you ask me. As you can see, regarding space as silent is an oversimplification. Sound can't travel through vacuums, sure, but for those who dare to listen, the universe reveals its own haunting symphony. It's just a matter of knowing where and how to lend an ear. Now, so far this video has recapped a lot of things we've covered in the past, but recently there have been some mind-boggling discoveries in outer space. In fact, every week there's a new breathtaking image released by one of our many telescopes on Earth and in orbit, or a new breakthrough that reshapes how we understand the cosmos. To stay on top of these, we've launched a weekly newsletter so you never miss the most exciting news, even if the headlines do. Sign up to the free Astrum newsletter with the link below. A new edition comes out every Thursday. Space is a desolate void, a vacuum where no sound can travel. So you might think that space is extremely quiet. You would be right, but only because you don't have the capability to hear anything with your natural ears. Turn your ears into radio wave receivers, and suddenly space is a constant symphony of strange and interesting sounds. I'm Alex McColgan, and you're watching Astrum, and together we will find out what the sources of these radio waves are, and what they sound like. We don't have to go too high above Earth to already be in space. Only 160 kilometers up, and sound can't be heard anymore because there aren't enough particles for sound waves to travel. But even here in space, there are plenty of other waves to be found. The ones particularly interesting to us are electromagnetic waves, which don't require other particles to travel like sound, but rather travel by themselves through photons. You are witnessing a form of electromagnetic radiation right now in the form of visible light by watching this video. However, visible light is just a tiny section of the total spectrum of electromagnetic radiation. It stretches from waves with extremely high frequencies to radio waves, which have waves sometimes kilometers long. There are observatories that look at all these different wavelengths, and this channel has focused normally on frequencies higher than infrared, as they can easily be converted and visualized in visible light. But there are also radio observatories, some orbiting Earth right now. And we're going to check out what they have picked up in the way you are most used to witnessing radio waves at audio frequencies converted to sound. Being in Earth's Van Allen belt, or its large band of radiation surrounding the planet, and you'll already start to hear some very interesting sounds. These sounds are generated by energetic particles in Earth's plasmasphere, which are being tugged to and fro by the rotation of Earth's magnetic field. You see, there is a plasmasphere around Earth, containing clumps of ions and electrons. As Earth and its magnetosphere rotate, the magnetic fields push through these particles, accelerating them in a wave called a plasma wave, similar in a way to how disturbances in Earth's oceans can cause waves to form. You are hearing these disturbances in the form of radio waves as they pass by one of NASA's Van Allen probes. These are called chorus waves and are often heard during Earth's dawn, which is why they are found on this side of the planet. An amazing type of chorus wave closer to Earth is the whistler mode plasma wave, which sounds like space battles and laser fire.
These exist in the cold and denser part of the plasmasphere and are caused by electromagnetic radiation released by lightning striking in the atmosphere. These waves generated by these strikes can bounce around within the magnetic field of the Earth. And because higher frequencies travel faster than lower frequencies, that's why these chorus waves sound like they have a fall in pitch, like a whistle. Going further out from the plasmasphere, an opposite effect can be heard. This time, there is a rising tone, almost like a conversation between songbirds. It is thought to be caused by electrons moving towards the night side of the Earth because of magnetic reconnection in Earth's magnetotail, transferring their energy to the plasma as they collide with it, as can be seen in this simulation. In another region within the plasmasphere, we can find something called hiss waves. These are thought to be chorus waves which have leaked out from the inner plasmasphere. It sounds much more menacing and cold than the other sounds we've heard so far. I find these clips very interesting, as it's sometimes hard to comprehend waves you can't see. But sound adds a new layer of understanding when combining it with a visualization.
What does the sun sound like? It's a simple enough question, and one that comes with a simple enough answer. The sun is silent, of course. Because sound doesn't travel in a vacuum, to us, the sun sounds like nothing at all. But let's do away with simple answers. What if sound actually could propagate through space? Without a giant cosmic muffler between us and our closest star, what would we hear? Would the sun sing to us, an enchanting melody in our sky? Or would its noise be such a cataclysmic cacophony, it would instantly be the last thing we ever heard? Scientists actually have the answer. Through spacecraft like the Parker probe, which is currently making skimming orbits around the sun, they can detect the kind of pressure waves and particles emitted by the sun and can convert those waves into the sounds we might hear if space was capable of such propagation. And interestingly enough, not all of the sun sounds are the same. I'm Alex McColgan and you're watching Astrum. Join with me today as we listen to several different sounds made by the sun, recreated through clever science, because it turns out that these sounds may allow scientists to solve two of the sun's greatest mysteries. In our imaginary scenario, where space has suddenly gained the ability to propagate sound, we can now start listening to the sun all the way from Earth. Although the Earth is 152 million kilometers away from the sun on average, it's perhaps unsurprising to learn that the sun is very loud, easily audible from where we are. It would sound something like this. Just a reminder, there is no sound in space. This is a sound reconstruction, turning amplitudes and frequencies into sound waves, creating clips of what the waves might sound like to the human ear if an atmosphere were present. This soothing buzz has an almost electrical feel to it. It reminds me of generators, or perhaps even something vaguely radioactive, which is appropriate given that this is the sun we're talking about. The nuclear fusion going on inside the sun is equal to 3.85 times 10 to the power 26 watts every second. About 1 million times more than what humanity produces in an entire year. All of this power being created has an unsurprising knock-on effect on the volume of the sound the sun would produce. To get a sense of what this would be like, take the device that you're watching this on and connect it up to the speakers that they use at your next rock concert. then play this noise at full blast. At 110 decibels, this volume level is survivable for short periods of time, but would likely end up with the entire population of the planet going deaf if they weren't wearing earplugs as it plays in our sky non-stop. In fact, we can consider it extremely fortunate that we don't actually have to deal with this. Species would have probably evolved with no ears, as hearing would be pointless. If we get closer to the surface of the sun, that sound level grows exponentially, with some experts rating it at 270 decibels. Remember, decibels are a logarithmic scale, so every 10 decibels higher it goes, you have to multiply the sound level by 10. To get a sense of how loud this would be, 270 decibels is louder than our atmosphere itself can physically convey. There is a cap on sound at 190 decibels in Earth's atmosphere, as different mediums have different volume caps, due to some complicated quirks of wave amplitude and energy levels, which we won't go into here. The volume of the sun would be 100 million times higher than this cap. The sun is loud. Which is a shame, as some of the sun's sounds can only be differentiated when we enter that ear-splitting zone. By the time the noise of the sun has reached us, many of the sun's sounds have blurred into one, meaning we miss out on some of their fascinating intricacies. To gain a better insight into the sun, we would need to get closer, entering into that blisteringly loud zone of noise. So let's ignore the volume of the sun for now, and instead let's focus on its sound patterns. If we were to enter a spacecraft and head towards the sun, we would soon begin to hear a difference in the sound's uniformity. Rather than a constant buzzing, we would hear something like this. This is the sound of the solar wind. The sun emits a constant stream of charged particles that blasts out across the solar system, and its existence represents one of the sun's greatest enigmas to date. You see, it's tempting to think of this stream from starting inside the sun and blasting outward under the incredible force of all that nuclear fusion. However, by the 1960s, an important discovery had been made through observation. Although particles within the sun's atmosphere, or corona, were moving around with an average speed of 145 meters per second, particles outside of the corona were traveling at 618 meters per second. This meant that particles that had enough speed to escape from the sun's surface were drifting into space, and then something in the sun's corona was hyper-accelerating them from subsonic to supersonic speeds, firing them off. What kind of process or mechanism is doing this remains a mystery to this day. The corona contains a second enigma too. It is far too hot. Although you might expect the center of the sun to be the warmest part of it, and the temperature to gradually go down the further from the center you go, this stops being true once you enter the corona. The surface of the sun has an average temperature of 5,600 degrees Celsius, but within a few kilometers, the corona suddenly sees the temperature jump to as high as 2 million degrees Celsius. Something in the sun's corona is flicking solar wind into space, and something is making things very hot. Scientists do not know why this is happening either, although it is thought to have something to do with magnetic fields. It's here that we would meet the third sound of our tour of the sun. As our spaceship would draw closer and we passed over the boundary between the corona and empty space, something known in science as the Alphen surface, we would begin to hear the following. These are known as Langmuir waves. They are formed by tiny oscillations of plasma particles vibrated by light itself as they stream from the sun through tiny funnels on the sun's surface, a magnetic equivalent to the sound a kettle makes when it boils. We have entered one such stream. Countless of these streams fire out from the sun's surface. The sun's exterior is covered in islands of hot material rising from the star's center. Once there, the material cools and sinks back into the star's mass, along the island's edges, and something about this process of rising and falling material, or something going on within the sun itself, makes these sinking zones stream out powerful magnetic field lines. Plasma is scooped up by the magnetic force and is sent streaming into space, the starting point of the solar wind. Scientists don't know what causes this process, but the sound of Langmuir waves is eerily beautiful. As the winds head out, not all the waves created in this way travel at the same speed. This has the effect of spreading out sounds, as faster parts of the wave run ahead while slower parts of the wave fall behind, creating what are known as dispersive waves. Such waves are filled with chirps, little eddies of sound where fast waves coming from behind meet slow waves already travelling ahead. Eventually, this evens out into the hum we heard at the beginning. There is one last sound that might offer an insight into the entire mystery, one that has some intriguing implications. Here, right within the sun's boiling corona, we can finally begin to detect Whistler mode waves. Whistler waves are the distant echo of high energy events that ring through the plasma of a celestial body's magnetosphere. We get them on Earth. Whenever lightning cracks, you get more than just thunder. A ripple travels through the planet's magnetosphere that can be picked up kilometers away if you have the right detectors. To truly get a sense of the scale of these waves, here is what they sound like on Earth. Just a few small little cracks and whistles, nothing too special. Now, here's what they sound like on the sun. To go from sparse, brief clicks to a cacophony of wailing wind indicates that the sun's magnetosphere is not just experiencing the odd crack of lightning. Something is going on constantly, all over, merging individual moments together into one incessant roar. Scientists are still trying to figure out what that roar is being caused by, but at least one theory for the force behind this sound, which can account for the dramatic acceleration and superheating of matter within the corona, is a dry-sounding little event called magnetic reconnection. Magnetic reconnection sounds fairly innocuous, and yet its innocent, technical-sounding name disguises a cataclysm. The sun is a tensely wound-up ball of shifting magnetic field lines, all due to that churning plasma within its heart. I cannot stress enough how powerful these are. When magnetic field lines travel away from the sun, it's sometimes possible for them to merge with other field lines, causing some of those iconic loops to form that you've likely seen in images of the sun before. However, at the moment such arcs are formed, all hell breaks loose. When two parallel lines touch, creating an arc, there's a massive realignment in the excess field line's polarity. Everything above the arc needs to find a place to go to ensure magnetic equilibrium is maintained. Cut from their tethers, the field lines further out from the sun form an arc of their own, which then catapults off into space like the releasing of a gargantuan stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees in seconds. Scientists have only recently developed the capability to be able to even see nanoflares, and aren't entirely certain the nanoflares they've seen are indeed the hypothesized events they were expecting, although they do seem to be accompanied by the expected superheating. This is an explanation that is still being worked out. Most of it is not yet understood. And still, it's not completely far-fetched that such moments when the sun gets so wound up it snaps explain why its corona is as hot as it is, and why it is flinging solar winds out across the solar system with quite the force we witness. Although, to go from a single crack into the roaring wail that we hear and to account for the constant solar wind travelling outwards in all directions from the Sun, nanoflares, or whatever the force behind this phenomenon is, must be extremely widespread throughout the entire corona. The Sun continues to hold many mysteries. The Parker Solar Probe, which collected many of these sounds, continues its journey around the Sun, gathering valuable data with every pass. The Parker Probe is only 4 years into its 7-year mission, so hopefully it will collect plenty more information for scientists to pore over. Perhaps they will find more sounds for us, each one a clue to the ancient riddle of how the universe works. Because ironically, just like listening to the ticking of a clock to try and figure out how the clockwork functions, the secrets to the Sun might one day be solved by what we hear rather than by what we see. Did you think space was silent? Well, it might be for audio or compression waves. But what if you were in orbit around Saturn, listening for radio and plasma waves? The Cassini spacecraft, which orbited around Saturn for 15 years, had a radio and plasma wave science instrument on board that could pick up what you are hearing now, being emitted by Saturn and its moons. These radio waves have been compressed for our benefit, converting roughly 30 minutes worth of radio waves to a minute's worth of audio waves. This wasn't just done to create a creepy audio file, but it had real scientific purpose, which was to examine the source of these radio waves. In the case of this audio file, the source was Saturn's aurora. You see, the Sun is always blasting out bits of its mass in the form of electrically charged particles, called the solar wind. Planets with a magnetic field surrounding them redirect this solar wind around the planet to its poles, where the charged particles impact the planet's atmosphere, or more specifically, its ionosphere. This impact causes particles in the atmosphere to become excited, or in other words, the collision ionizes the particles in the atmosphere, causing them to emit electromagnetic radiation. We can see this ionization with our own eyes in visible light, but aurora also emit radio waves, which we need special instruments to detect, like the one that was on Cassini. These radio waves bounce around within the planet's magnetic field, which is where Cassini picked them up. How do we know this? Through another audio file. What you are listening to here is the Cassini spacecraft passing through the bow shock of Saturn's magnetosphere. As I mentioned, Saturn has a large magnetic field surrounding it, called the planet's magnetosphere, which deflects the solar wind around it. For the first section of the audio, Cassini is outside of Saturn's magnetosphere. Outside the magnetosphere, radio sources are quiet, and there is calm in the audio. Then, Cassini's orbit takes it through the magnetosphere's boundary, called the bow shock, which is the place where the magnetic field and the solar wind collide. There is a sudden increase in radio waves. Past the bow shock, Cassini begins to detect a lot more radio waves bouncing around Saturn's magnetosphere, noticeably different from the outside of the magnetosphere. But Cassini heard a lot more than just aurora. Cassini also made some close approaches to Saturn, listening closely to the planet itself. Saturn has a thick and dynamic atmosphere, with massive storms spanning the planet. One such storm sounded like this.
What you are listening to here are radio waves being generated by lightning in one of Saturn's storms. It may sound small and almost puny, but remember that this is not the representation of audio you're hearing. These lightning strikes are so powerful that Cassini could detect their radio waves in space. To give you some kind of scale, scientists estimate that the lightning in Saturn's storms are roughly 1,000 times more powerful than typical lightning on Earth. To get this close to Saturn, Cassini had to pass through its rings. During flybys like this, Cassini listened. What do you think could be the cause of this audio? Cassini was travelling extremely fast around Saturn, as fast as 121,000 kilometers per hour. As it orbited through the Janus Epimetheus ring, a very faint and dusty ring, it would impact tiny particles, which would vaporize into clouds of plasma. These tiny charged explosions could then be picked up by Cassini's radio and plasma wave science instrument, and these impacts were then converted into the audio you are now hearing. The increased frequency of these impacts showed the densest part of the ring, and as the impact subsided, it indicated that Cassini was moving away from the ring again. Cassini tried this again later in the mission, except this time through a gap between Saturn and the D-ring. You'll notice this time that there wasn't a noticeable increase in collisions. At first, scientists thought that this was because the gaps between the rings were just really barren of particles. However, a second orbit through the gap revealed something different. This time, and every orbit after that, there was a noticeable increase in particle collisions. So what happened the first time? Well, as it turns out, there were particle collisions, but none of the particles in that part of the gap were big enough for the RPWS instrument to detect. Cassini had another useful instrument on board, however, called the Cosmic Dust Analyzer, which could detect particles up to only 1/1,000,000th of a millimeter in size, and this instrument did detect an increase in particle collisions during the fly-through. After passing the ring during the second fly-through, you'll also notice these rising tones. Scientists are unsure what causes these exactly, but it is reminiscent of what Cassini detected earlier in the mission. The other most interesting source of radio and plasma waves around Saturn is actually its moon Enceladus. 2 weeks before Cassini plummeted into Saturn's atmosphere,
It captured this as it passed by Enceladus. These observations show that Enceladus and Saturn have a plasma circuit between the two, much like Io and Jupiter, just perhaps to a lesser extent. Although the strength of this plasma circuit surprised scientists greatly. Cassini was also equipped with a magnetometer. This is what it detected by Enceladus. During the flyby of Enceladus, it was able to detect a bending of the magnetic field, indicative of a thin atmosphere, the source of which is likely to be the jets and cryovolcanism near the south pole of the tiny moon. This geological activity draws parallels again to Jupiter's moon Io. The magnetic fields of both planets interact strongly with the ejected atmosphere of the moons, creating a flux tube, or a current of charged plasma particles. There's just one more place that I want to have a look at around the Saturn system, and that is Titan. Cassini's first major objective upon reaching the Saturn system was to launch the Huygens probe towards Saturn's biggest and perhaps most interesting moon, Titan. Although Huygens didn't have its own RPWS instrument, it did have some other instruments. See if you can guess what this is a recording of as it descended towards Titan's surface. If you guessed radar echoes, well done. Huygens used this to determine its altitude above the surface. And what about this? This is perhaps the most impressive of any of the clips I've shown so far. Why? It doesn't sound that impressive until you realize that this is actual audio taken by a microphone on the Huygens probe as it descended through Titan's atmosphere. This is it leaving the vacuum of space and diving into another world. What you are hearing is exactly what you would have heard if you had been sitting on Huygens as it descended. This gives the clip such an awe and perspective like nothing I've heard before. Somehow it's quite incredible for me to think about. We often have visuals of other planets, but I'm not really sure if there's anything quite like this out there. And there we have it. The sounds of Saturn and a couple of its moons.
Having the sun as your neighbor is hard. Searing hot temperatures, deadly radiation, and the onslaught of meteor collisions don't exactly make it the most welcoming part of the solar system. As you can imagine, these challenges make Mercury a particularly tricky place to get to. For this reason, even though it's much closer to us than Jupiter or Saturn, Mercury remains relatively unexplored. Still, scientists managed to send 2 different missions out to study Mercury. Mariner 10 flew by in the 1970s, followed by NASA's Messenger in 2015, which was the first probe to ever successfully orbit the planet. And now, as I speak, a third Mercury mission is hurtling through the constellation of Pisces over 177 million kilometers away from Earth. Bepicolombo, a labor of love between the European Space Agency and the Japanese Aerospace Exploration Agency, is set to arrive on December 5th, 2025. It will carry out a comprehensive study of the planet's magnetic field, surface, and internal structure. But, as they say, the journey is the destination, and Bepicolombo's journey is a long one. I'm Alex McColgan, and you're watching Astrum. Join me today as we reveal what Bepicolombo has revealed of Mercury so far, why it's traveling farther than the distance of Pluto to get there, and what we're hoping to learn about the closest planet to the Sun. On October 20th, 2018, Bepicolombo took off from the French Guiana Space Center, beginning its 7-year journey to Mercury. Its trajectory would take it around the Sun 18 times, including 9 planet flybys. The first was an extremely close flyby of Earth on April 10th, 2020. Bepicolombo came within just 12,700 kilometers of our planet's surface, about the distance from Copenhagen to Santiago, Chile. Its journey will then take it on 2 flybys of Venus and 6 of Mercury, the last 3 of which are due to happen in September, December, and January of next year. In total, the mighty spacecraft will cover a distance of 8.5 billion kilometers. Taking such a long route was the only way Bepicolombo could slow down enough before approaching Mercury's orbit. But why is slowing down so important? Well, if the spacecraft arrived with too much speed, it would swing right past the planet and get sucked into the Sun's powerful gravitational field instead. Bepicolombo was designed to complement and deepen the findings of its predecessor, the Messenger probe. While Bepicolombo carries many of the same instruments as Messenger did, it is equipped with higher caliber tools able to obtain larger ranges of data. Additionally, Messenger's orbit of Mercury was rather one-sided. Its periapsis was over the South Pole, meaning we have great detail and mapping of the Northern Hemisphere and almost non-existent data on the Southern Hemisphere. Bepicolombo plans to rectify this by examining Mercury from an orbital angle more in line with the planet's equator. Bepicolombo is a very unique spacecraft. It's made up of 3 component parts, 2 probes and a propulsion module, which were launched and traveled together in a united configuration known as the Mercury Cruise System. Run by ESA, the Mercury Planetary Orbiter, or MPO, will study the planet's surface and interior, while JAXA's Mercury Magnetosphere Orbiter, affectionately known as MEO, will study the planet's suspiciously low magnetic field that has baffled scientists for decades. The name of MEO was actually chosen by the Japanese general public. It means a waterway, and according to JAXA, it symbolizes the scientific milestones reached so far and wishes for safe travels to come. MEO and the MPO sit either side of an interplanetary propulsion unit called the Messenger Transfer Module. Stacking the different parts of the craft together like this means most, but not all, of the scientific instruments on board will be inoperative until Bepicolombo settles into its orbit around Mercury. At that point, the MPO and MEO will be jettisoned from the spacecraft and go their separate ways to study Mercury from different vantage points. But don't worry, there's still enough data being sent back to keep us entertained. Why don't we take a look back at how far this mission has come, what it's already taught us, and explore some of the amazing things it's seen along the way. Bepicolombo's first encounter with Mercury came in October 2021. passing just 200 kilometers above the planet's surface, it sent back some stunning images. As it drifted past, Bepicolombo snapped Mercury's northern hemisphere. To the average person, it might look like our rocky, inert moon, but the trained eye sees the Calvino crater, which could hold the key to deciphering Mercury's crust composition. The Lermontov crater hosts traces of volcanic activity and mysterious pockets where an unidentified compound in the planet's crust is being lost to space, and scientists have no idea how or why. These images remind us just how enigmatic Mercury is, and how much we have left to learn about it. Another camera mounted on the spacecraft caught Mercury from another perspective, one that left the planet's volcanic history on full display. Previously lava flooded and over 250 kilometers wide, the Hayden crater comes into view, along with the Pampu Facula, one of Mercury's many bright spots, probably formed by volcanic eruptions from billions of years ago. Even though Messenger had already shown us Mercury's volcanic past, it's still pretty amazing that this activity left a mark visible after such an inconceivable amount of time. And Bepicolombo didn't just show us how the flyby looked, it captured how the flyby felt. You know how your phone has an accelerometer in it that helps it know when and how its orientation changes? Scientists mounted a similar accelerometer on Bepicolombo's MPO. It measured the movements and vibrations of the spacecraft as it flew past Mercury, creating a sort of sound map of the flyby. Scientists then plotted that data to frequencies us humans can actually hear, so you can actually hear the flyby. I'll play it for you now. Pay attention to the two distinct sounds towards the beginning. They represent the changes in solar radiation pressure when the spacecraft enters and then exits Mercury's shadow. The big clunk towards the end is the sound of the Phoebus instrument assuming its parking position. Here's the clip. Pretty cool, right? I've got another one, and it's even better. Bepicolombo captured magnetic field data during its flyby that was also later deciphered and sonified by scientists on the ground. This one is a little more abstract than the other, but we'll give it a go. You're going to hear two synthesizers at the same time. The first synthesizer changes pitch with the changing magnitude of the background magnetic field. A lower pitch means more intensity in the magnetic field. The second synthesizer changes pitch with the variations of the magnetic field magnitude. A more turbulent magnetic field is represented by a faster change in pitch. The dotted vertical line shows where the closest approach was. After the closest approach, you'll hear something that sounds like a DJ scratching a disc. Lots of fast changes in pitch. That right there marks when the spacecraft crosses the magnetosheath, where the magnetic field is highly turbulent. Let's have a listen. On June 23, 2022, just over halfway in its planned journey, Bepicolombo crossed paths with Mercury once again. This time, the spacecraft turned its gaze towards Mercury's largest impact crater, Scariest Basin. At a whopping 1,550 kilometers wide, it's actually one of the widest known craters in the solar system. Scariest Basin was likely created by the collision of a comet, asteroid, or other celestial object some 3.9 billion years ago. The highly reflective lava craters on its floor make it easy to see as the bright semicircular area of Mercury's disk below the magnetometer boom. The second flyby gave us beautiful images of Mercury's craters like we'd never seen before, like this one of Hyäni, a crater embedded in smooth volcanic plains, potentially near an ancient volcano which Bepi Colombo plans to examine when it finally settles into orbit. Almost exactly a year later, on June 19, 2023, Bepi Colombo reapproached Mercury from a height of just 263 kilometers. The flyby images captured the 600-kilometer-long Beagle Rupees, one of the many lobate scarps on Mercury that was first imaged by Messenger in 2008. Other than our moon, Mercury is the only planetary body in our solar system known to exhibit this tectonic signature. When the interior of the planetary body cools, it leads to a global contraction and surface expression of a thrust fault, aka a lobate scarp. Beagle Rupees has an especially pronounced curvature, more so than other scarps on Mercury, offering geologists a rare insight into the planet's tectonic history. As a result of the third Bepi Colombo flyby, a large 218-kilometer wide peak ring impact crater received the name Manly after 20th century visual artist Edna Manley. The original basin floor was flooded by lava, giving the crater its visibly smooth interior texture. Bepi Colombo will explore Manly crater further from orbit, seeking to measure its carbon composition and detect other minerals that may be present in order to learn more about Mercury's geological history. Gliding past Mercury on its most recent flyby, Bepi Colombo snapped a series of farewell Mercury images. At 236 kilometers from the surface, Bepi Colombo appears to hug the planet goodbye. Scientists back home on Earth will have to wait another 16 months for the next set of images. Now, these flybys are more than an indulgence for our senses. They also revealed important nuances of the planet's particle environment and magnetic boundaries. One of the instruments aboard the MPO probe is Phoebus, probing of Hermian exosphere by ultraviolet spectroscopy. Phoebus uses UV emission from Mercury's exosphere, the planet's outermost and only atmospheric layer, to determine its composition, structure, and interactions with the surface. It does this by detecting specific types of light emissions in the ultraviolet spectrum, ranging from 55 to 350 nanometers. By capturing these light emissions across the whole spectrum, it helps us figure out what the exosphere is made of and how its particles are spread out. As Bepi Colombo emerged from Mercury's shadow, Phoebus detected the presence of hydrogen and calcium, confirming earlier findings from Messenger that established the presence of calcium in the planet's exosphere, particularly around the equator and on its night side. Interestingly, this is the opposite of the distribution observed for sodium and potassium, which more readily concentrate around the poles. Once in orbit around Mercury, Phoebus will be able to send back much more detailed analysis of Mercury's exosphere, composition, and dynamics, including how it changes with location and time. Speaking of Messenger, back in its day, it discovered ice on Mercury's North Pole. Bepi Colombo will continue this legacy by continuing the search for ice in permanently shadowed regions of high latitude craters. As you might know, Mercury is the only planet in our solar system to have a magnetic field similar to Earth's. Thanks to its liquid iron core, Mercury exhibits a dynamo effect, which creates an innate magnetic field around the planet. However, Mercury's magnetic field is just 1.1% that of Earth's magnetic field, leaving scientists fascinated with how it's generated. One of the big goals of the Bepi Colombo mission is understanding this magnetic field better. So far, the only magnetic activity of the Northern Hemisphere has been mapped by NASA's Messenger mission. Scientists hope that Bepi Colombo will be able to shed light on the dynamics of the planet's magnetism in the Southern Hemisphere. This magnetic field is of great importance. By understanding it, scientists aim to shed light on Mercury's origins, its evolutionary journey, and the current state of the planet's interior. MPO and MEO will travel through different areas of Mercury's magnetosphere on different timescales, simultaneously measuring how the magnetic field changes over time and space, and its relationship to the powerful solar wind. All this new data from the Bepi-Colombo mission will eventually be compared with global magnetic field models from the Messenger mission to build the most accurate picture yet of Mercury's magnetic field, which could unlock telling insights into the planet's elusive past. As we await Bepi-Colombo's next flyby in September 2024, the journey to understanding Mercury continues. The spacecraft is gearing up for its next major maneuver, a prolonged solar electric propulsion thruster arc planned to begin in early August, and it should last until mid-September. Thruster arcs, along with strategic flybys, help Bepi-Colombo break against the enormous gravitational pull of the Sun. This is the only way to successfully insert into orbit around Mercury when the time comes. Once in orbit in December 2025, the real exploration begins. Mercury's heavily cratered surface records a 4.6 billion year history of asteroid and comet bombardment, which together with unique tectonic and volcanic curiosities will help scientists unlock the secrets of the planet's place in solar system evolution. Bepi-Colombo is set to remain in orbit around Mercury for 1 year, and if all goes well, might get the green light for an extra year on the mission. Scientists hope to study the planet like never before, from its composition to its geophysics, its atmosphere and magnetosphere, both its history and the history of other inner planets like it, including Earth. Until then, we've got a few more flybys to look forward to, and the haunting pictures they're bound to capture for us Earthlings back home.
If you were paying attention to the news last year, I don't think it was possible to miss the media hype about the NASA InSight mission to Mars. But after it successfully landed, there's hardly been any mention of it since. So what were its mission goals on the Martian surface? And has it achieved anything now that it's been there for almost a year? I'm Alex McColgan, and you're watching Astrum, and together we will find out exactly what InSight has discovered on Mars so far. Let's begin with a quick recap of the mission. InSight launched from Earth in May 2018 and landed on Mars in November of the same year. Unlike a lot of the other NASA missions to Mars, this is a robotic lander, not a rover. In fact, it shares a lot of similarities and technology with a previous NASA mission called Phoenix, although they had quite different science goals. InSight's main objective is to investigate the seismology of the planet, whereas Phoenix was more interested in the past and present habitability of Mars. The last thing you probably saw of the InSight mission was this image, the first image InSight sent back to Earth. But there have been a lot of interesting things that have taken place since then, so let's see exactly what happened after it landed. The first thing InSight did was send back signals to Earth that it had touched down safely and sent the famous first image. As you can see, a lot of dust had been kicked up by the landing, as InSight used descent rockets to slow its fall. A camera pointed under the lander reveals the effects of the rockets, which carved out mini craters under the craft. InSight was programmed to wait a few hours for the dust to settle before deploying its 2 circular solar panels, as dust settling on the panels themselves would affect the efficiency. InSight quickly began collecting data, even before deploying any of the science instruments. The first thing it recorded was the Martian wind, picked up by vibrations sensed by the seismometer still on the lander. And this is what it sounded like, although I should note that you will probably either need a subwoofer or headphones to hear this. This has not been sped up. These are literally the vibrations caused by Martian wind going over the solar panels of the lander. The frequency of the vibrations converted to audio. For the benefit of those who can't hear it, here it is pitched up by 2 octaves. InSight can also detect changes in air pressure. Here is the air pressure changing as wind blows across the lander. This audio has been sped up by a factor of 100 for it to be within human hearing range. What is fascinating though is that we don't have to just imagine the wind passing by InSight, as it was also able to capture footage of water ice clouds passing by overhead, visibly showing the direction of the wind. Yes, although Mars is currently a barren wasteland, there is still a tiny amount of water vapor in the atmosphere. Almost immediately after landing, InSight was taking 3D images of its surrounding area in order to find the perfect spot to place the seismometer. Based on those 3D images, NASA recreated this area as accurately as possible, even going as far as using the HoloLens augmented reality headset to match up the surface of Mars with the environment they were recreating. The seismometer is extremely sensitive and had to be placed directly on the surface, avoiding any rocks that would affect the placement of it and of its windshield. As you've already heard, wind is easily detectable by the seismometer, so the windshield had to fully enclose it to protect it from potentially contaminated measurements. Once the go-ahead was given, InSight carefully used its robotic arm to place the seismometer on the surface of the planet. From there, it could detect the faintest vibrations, from Marsquakes to meteors impacting the surface close by. But what is the point of all this? Well, when a specific part of the surface of a planet vibrates, a ripple propagates through the planet's interior. Listening out for the echoes, scientists can determine the internal structure of Mars. They would then correlate the data collected with the other main scientific instrument on board InSight, namely the Heat Flow and Physical Properties package, which is a combination of a drill and a hammer with a very accurate temperature sensor to measure how efficiently heat transfers through the Martian core. The mole, as they call it, tried to dig 5 meters down, taking temperature readings every 10 centimeters, extrapolating these readings to estimate the thickness of the Martian crust. Unfortunately, the mole got stuck only 30 centimeters down and is currently unable to recover. It probably hit a very hard rock, or the soil simply didn't provide enough friction, which tilted the mole before it had fully exited its housing, getting stuck in this position. Again, ground-based teams tried to replicate the problem and look for a safe way to pick up the housing around the mole and use the robotic arm to straighten its course. Putting their plan to action on Mars, the operation was successful. The housing was lifted off, exposing the mole, but no further progress has been made as of this moment. Latest plans are to try and use the robotic arm to push down on the soil right next to the mole, hopefully giving it the friction it needs to start digging deeper, if friction really was the problem. Luckily, the seismometer was more successful. In April of this year, it detected its first Marsquake. And this is what it sounded like. Again, the vibrations have been sped up by a factor of 60, as the frequency would not be audible to the human ear. While data like this doesn't need to be converted to audio for scientists to use, it is useful for the layperson so they can better grasp what is going on. What you will notice though is how sensitive this seismometer is. Even under the windshield, it still picks up vibrations caused by the wind. And even the robotic arm moving can be easily detected even though it's a few meters away. Lastly, InSight is acting a little like a weather station on Mars, with instruments detecting wind, air pressure, and air temperature. As you can see, even at the equator, Mars is a chilly -25 degrees Celsius at its warmest at the moment, bottoming out at -100 degrees Celsius. We are also seeing some gusts of up to 60 kilometers an hour, and low air pressures, about 6 millibars compared to Earth's 1 bar. So there you have it. As you can tell, InSight has had some ups and downs, but the overall health of the lander is good, and it will hopefully be collecting data for a while yet, assuming not too much dust settles on its panels. This data will provide a more and more accurate 3D model of the interior of Mars, providing evidence of what Mars once looked like and how it formed in the first place. And if the mole can get functioning again, we'll be able to get data for the heat flow under the surface too, to find out if there really is an active mantle under the surface still or not. So keep an eye out for this mission in the coming months and years. Venus is probably the least hospitable planet in the solar system, and as a result, it is not often the target of space missions. However, even though it wasn't particularly designed for it, the Parker Solar Probe has had a few glimpses of our sister planet. Parker regularly uses Venus's gravity to get into a tighter orbit around the Sun, and in July 2020, its orbit took it only 800 kilometers from Venus's surface, within its upper atmosphere. The last time this happened was in 1992 with the Pioneer orbiter. Listen how Venus's naturally occurring radio signal changes when Parker enters the ionosphere. Using this data, scientists were able to confirm that the density of Venus's ionosphere changes in response to the 11-year cycle of our Sun, but they've yet to figure out why. Solving this puzzle could help us understand why Venus ended up so different to Earth. As you probably know, sound can't travel through the vacuum of space. However, there is a process to turn scientific data into audio called sonification. While this may not have huge scientific implications, it does help us see space in a new way. Now, you may think this is weird, but I want you to close your eyes and listen carefully. I'll tell you when you can open them again. Eyes closed. This beautiful piece of music is not randomly generated, not composed per se, but is the sonification of an image of the center of the galaxy, a 400 light-year region of space around the supermassive black hole Sagittarius A star. Now listen again and I'll give you a context to what you are listening to. The translation of the image goes from left to right. Each ding you hear is a star, differing each time depending on that star's brightness and size in the image. The gas and dust structures found near our galaxy's center fill the image, producing much longer, droning sounds. Now, imagine you were blind from birth. What you are listening to now may have just been your first experience of what space could look like. Truly, you can get a slight appreciation from just this of the vastness of space and how fully it is occupied by celestial bodies in just 400 light years across. Now, open your eyes. Is this image how you imagined it looking? Shut your eyes again throughout the rest of this video. This particular image is a composite image of various wavelengths of light, taken with a number of different telescopes, Telescopes are instruments that are designed to pick up different wavelengths of light, and adding them together in this case creates the full image. Just like how the combination of different instruments playing their own lines in an orchestra creates a beautiful musical composition. When we separate the lines of the piece, or in other words, separate the wavelengths of light, we hear the image differently. If we focus on the Chandra X-ray telescope's view of the same region, the image sounds a lot emptier. The main focus of this line of music is the superheated gas surrounding the supermassive black hole found in the center of our galaxy. It's the noisiest source here, building up into a crescendo as we pass over it. The Spitzer telescope's music of the infrared showcases not only more stars, but the hum of cooler, complex dust structures that are also much more apparent here. And lastly, the music of visible light through the Hubble Space Telescope. The droning sound here is from the particularly dense regions of dust and gas structures, where star formation is actively taking place. Put them all together, and we have our composite image again, and our full orchestral piece. This process can be done with many different images of space. Do you know of the supernova remnant Cassiopeia A? Well, whether you know it or not, try and guess its structure from just listening to the sonification of its image, this time from the center of the image outwards. There's no ding sounds this time, as there are no stars in this image, just the ups and downs in intensity of the nebulous structure. And what about this? The pillars of creation from left to right. There are the occasional stars here, and the location and intensity of the nebulous structure can sort of be imagined. So there we have it, space in sound form. And maybe an insight too as to how you could experience space if you were blind. Were you good and you only opened your eyes when you were supposed to? I suggest now watching over this video one more time with your eyes open to visualize and give context to what you are hearing. It may surprise you. Thanks for watching.
I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team.
Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.